Assalamu alaikum. Welcome to another lecture of operating systems. Today we will talk about scheduling. Now, this particular lecture specifically talks about one of the earliest scheduling frameworks, which is first in, first out, shortest job first, shortest time to complete first, and then round robin. Now, specifically, we'll be introducing two metrics as well to discuss which framework is better than the other one. Now, some assumptions with respect to workload. Now, a workload is defined as the processes which are currently running in the system. Or for students, for instance, your workload is the number of courses that you're taking a semester. For a faculty, the workload would be the number of courses you're teaching a particular semester. Similarly, workload within operating system means the processes which are running in the system. Now, the processes are also sometimes called jobs. Now, before we begin talking about different scheduling frameworks, let's make some assumptions. And those assumptions don't need to be true, but let's set them. And as we teach additional chapters, you'd realize each of these assumptions would be relaxed and newer frameworks will be discussed. For instance, next chapter, we will only be discussing about multi-level feedback queues, which is, one of the, which in fact won a top Turing Award for that particular scheduling framework. Now, currently, our assumptions are all jobs arrive at the same amount of time, at pretty much all jobs arrive at the same time. All jobs only use the CPU, that is, they don't perform any input-output. So a job may move from a running state to a ready state. If it performs input-output, you would say it's blocked. But towards the end of this discussion, we would relax that. And all jobs run pretty much almost for the same amount of time. You would see we would relax that a little bit to discuss certain other things about scheduling frameworks. And here is the most important one. The runtime of each job is known. Now, generally, that's not true, but only for this chapter, let's just assume that the scheduler knows how long will each job run. Now, the turnaround time is the time it takes for the job to arrive, the difference in the time it takes for the job to arrive as opposed to the time it takes for the job to complete. So that would be the turnaround time. So, for instance, if you come to a bread shop, right, the turnaround time on average would be measured in, from the point in time when you arrive at the shop to the point in time when you get the bread that you need or the naan that you need and you leave. And you average around all the customers, let's say, that come during the day. Another metric is called fairness. And a lot of times performance metric, which is the turnaround time, often is at odds with fairness, okay? Fairness, in some sense, you could say, the first come should be the first person to be served. Now, imagine you're at a tire shop, and it's interesting to note because this happened to me fairly recently that I just needed to fill up my tires. I asked the guy to, right now I have a tire pressure of 20. Can you fill it up to 30? And it takes just only 2 minutes to fill up all 4 tires. The guy actually asked me, the person before you came first, and he was getting his entire tire fixed. So the tire was punctured. He had to put a puncture there, and then he had to take out, put the tube back into his tire and put the tire back into his car. It was going to take me about 20, it's going to take him about 20 to 30 minutes. But my 2-minute job had to wait for about 30 minutes. So I ended up leaving that shop and going to another shop. So, I mean, it was fair because the first person, he came before me. But is that a performance metric? Should a 2-minute job wait for a half-an-hour job to finish? But that's something we would consider over the course of time. Now, the first idea is this thing which is called first come, first serve. It's very easy to implement. The idea is whoever comes first, gets the job done first. And it is easy to implement by that very fashion. So, for instance, in this case, let's just assume that A arrived a hairline just before B, which arrived a hairline just before C. Now, you can see each job, because A arrived first, A gets to use the system first, and then A completes the job. It really fully completes the job. Then there is a context switch, and then B takes up, B completes the job, and then C takes up, C completes the job. Now, the average turnaround time, because A came at 0 and A finished at 10, so that's 10 seconds. B came at 0, so arrival is 0, but the completion is 20, so that's 20. C again came at 0. They all arrived at the same time, but a little before B, a hairline before C. So C arrived at 0 but completed at T, so the average 30, so the average turnaround time is 20 seconds. Now, the problem with first come, first serve, or first in, first out, FIFO, is that what happens if A arrived before B and it was a way long process? This is what is referred to as a convoy effect. So, for instance, if A arrived before B and B arrived before C and A was a long job, then you can see here you give A the full system until A completes the job. And then you allow B to work, and then you allow C to work. Now, FIFO is easy to work, but as you can see, because of the convoy effect, when A arrives at time point 0, it finishes at 100, so the turnaround for A is 100. Now, B arrived a hairline before A, and it is a short job. But because A had to complete first, B finished at 110. So the turnaround time is 110. And C arrived at 0, but it finished at 120. So the turnaround time is 120. You take the average of 3, it comes out to be a whopping 110 seconds, which is not good at all. It's not good at all. So FIFO, although easy to implement first in, first out, functions fairly poorly if either of the job runs for a very long duration of time. If the first job, for instance. So how can we improve this? Well, the idea is because, remember, we are making an assumption that we have an idea of how much time each job takes. So the scheduler does receive A, B, and C almost at the same time. It puts it in a queue. And because B and C have the shortest time to complete, you say, I'm going to run B first because B arrived, and then I'm going to run C because B arrived before C. I'm going to run A last. And the reason for that is because, again, the assumption here is that I know how much time it takes. And that assumption is not entirely true. But for right now, we're going to assume, well, we do have an idea how long does each job take, and therefore we're going to run B and C first. So now if you run B, you can see, well, B arrived at timestamp 0, and it finished at 10 seconds. So that's 10 for B. And then C arrived at time 0 and finished at 20. So that's 20 seconds for that. And A arrived at time 0 and finished at 120. So now that's 120 over there. You average it out, it's 50 seconds. Now that's very good compared to 110 seconds. It's almost 2 times improvement. Okay. Now, that's the shortest job first. But what if, and this is interesting, what if, Right now, the assumption was, A, B, and C came almost at the same amount of at the same time, and therefore, the scheduler had the privilege to choose B and C first before A. But what if A came first and B and C came, let's say, 10 seconds later, as is the case here? A came at 0. Now, when A comes at 0 and there is no B and then there is no C, well, then is the only job left, and the system can't just wait and say, I'm going to wait and see if another job comes and then I'm going to decide. No, A starts there and then. So when A starts, it takes about 100 seconds to finish. B and C arrive at 10, timestamp 10 here. And so B finishes at 110. So 110 minus 10, that's 100. And then phi finished, finished at 120. So 120 minus 10, that's, again 110. You divide all of this by 3, that's 103.33 seconds. Not a lot of improvement, you can see. So yes, it does improve significantly if jobs do arrive at the same time. But if a long job is the lonely job that arrives first, we actually don't there isn't much improvement. There's hardly any improvement between 110 seconds that you see here and then 103 seconds that you see here. So there's another one which is called the shortest time to complete first. And this is preemptive shortest job first. It says, I'm going to start, if there's only one job, I'm going to start it, obviously. You're the only customer that I have, might as well start serving you. But as and when more customers come in, I'm going to start, giving them facility. For instance, let's say you come to a naan shop, you're the only customer there, and you order 20 naans. The guy starts serving you. He starts putting in naans into his oven and he starts baking them up. And then comes along your friend with just one naan. Well, he can give that one naan to him and then he can go say good farewell and he can still serve you. So that's like the preemptive part of shortest job first, and that's called shortest time to complete first. Now, here, obviously, you start A because there was no job except A. So A was your only customer and you start serving him. But 10 seconds later, B and C arrive. Now, when B and C arrive, because, the oracle says right now, we do know how much time it takes to complete a job. Again, that's not entirely true, but we're going to assume that is true for now. So as B arrives here, you're going to say, well, because now I have A, B, and C, all three lined up in my queue, I know A takes a long time, and B takes a short time, and C takes a short time. But B came before C, so I'm going to run B first, and then I'm going to run C, and then I'm going to run the remainder of A. Imagine if you have 20 naans to serve, and B requires just one, and C requires just one. Might as well give B and C, make them happy customers. You don't lose much either. Okay. So A doesn't lose much either, but it's a little unfair for A, but it's okay. A can deal with it. Now, but I mean, it's equity as opposed to equality. So now here A started, but then B arrived at 10 and B finished at 20. So that's 10 seconds. So you see 10t minus 10 over here. And C arrived at 10, but finished at 30. So you have 30 minus 10, which is for C here. But A arrived at timestamp 0 and finished at 120. You see 120 over there. Averaged all out, it comes to 50 seconds, which is very good. Okay, so you can see you started with the basic approach, which is FIFO, and then we realized it doesn't really help for a convoy effect. So what about we do a shorter job first that really increased it from 110 to, let's say, 50 seconds, and then realize, well, the convoy effect is still there if ARI happened to be the lonely job out there. So now we improved it further and we've said, let's do the shortest time to complete first, which is a preemptive version of shortest job first, which really does improve. So now there's this another metric. The first was the average turnaround time, which was the time, the difference between when a job arrives as opposed to when the job finishes. That was the turnaround time. And you average it out over the number of jobs that you have. But then you move forward with another metric, which is called response time. Response time is, how do you quickly respond to a new customer based on whatever their requirement is, whatever the demand is. So the response time is the time difference between its first run and its time of arrival. Okay? And this is important. Can we build a scheduler that has a good response time? Now, this is different from the turnaround time. Okay? So the turn response time would be, you go to a restaurant and you want your order to be taken first. I mean, you want as minimum time to pass between you being seated in the restaurant and somebody takes your order or somebody gives you a menu, for instance. But if you have to wait a very long amount of time, even just to receive the menu, then it's going to take you even longer time to, get the job done. So think about that, right? So the turnaround is the average time it takes you for you to get this meal served, as opposed to, you do like to get your menu on time. So there is something which is called round robin. And round robin is somewhat essential because the shortest job first, again, actually has a bad response time. Um, but the round robin offers a better response time, almost at the same amount of turnaround time. And it does so. And what round robin basically means, it says if there are three people, I'm going to go A to B and to C, and then cycle around again to A to B and to C, and then cycle around to A to B and C, serving them in parts until all of them get their jobs done. It does so using what is called a time slice or scheduling quantum, or you can see what. Um, so this is our example of the shortest job first, which is bad for response time. So, I mean, look at this. This is shortest job first. So A, B, and C have the same amount of time. They run for the same amount of time. A and then B and then C. So A star arrives at timestamp 0. It finishes at timestamp 5. You can see here the average turnaround time is not being recorded here. Sorry. So A arrives at 0 and it is responded instantly. That's why the response time is 0. B comes in at 0, but the first time the system started noticing it, the system ran it, was at timestamp 5, so that's why the response time is 5. And then C arrived at 0, but the first time the system laid eyes at it, let's say ran it, was at timestamp 10. So therefore, the response time is 5 seconds. Now, this is round robin. You can see the average turnaround time. You can see on the overall time it takes to finish all the three jobs is the same. Finish all three jobs is the same. But obviously, so here A arrived because the time slice is just 1 second. So A arrived first, A was looked on first, and then B was looked on, and then C was looked on, and then it goes back to A, and then back to C, and then back to C, processing it as, giving it, and then A, and then B, and then C, and then A, and then, and you can see here the response time now drastically improves. A arrived at timestamp 0, it was looked around, it ran instantly, and then B arrived at time 0, it started running at timestamp 1, and then C arrived at 0 and it started running at 2-second timestamp. So overall, it improved significantly. But if you calculate, let's say, the average turnaround time here, you can say for SJF, it is 5 plus 10 plus 15 divided by 3. That's 30 divided by 3, that's 10 seconds on average, right? It's 5 plus 10 plus 15 divided by 3, that's 30 divided by 3, that's 10 seconds. However, here, if you look at the turnaround time, average turnaround time, this is at timestamp 12. The time, the time it takes for A to complete is 13, actually, sorry, 13. The time it takes for B to finish is 14. And the time it takes for C to finish is 15. So the average is obviously 14. So the turnaround time here is better than the turnaround time here. Here, I mean, here it's 10, here it's 14, but the response time of round robin is significantly better. There is, however, a problem though, and the problem is context switch. So whenever you're switching from one job to another, you have to do some context switching. And the idea is if your time slice is really small, then the time for context switch actually takes more, because now the idea would be to amortize the cost of switching, which basically is having a longer time slice. But having a longer time slice means it does reduce your response time a bit. So there is a trade-off that you need to consider for a system designer as to what should be the time slice. But whatever it is, the cost of a context switch should not be more than 10% of the of this of the time slice time period. It should not be more than 10%. Okay, not be more than 10%. Okay. So let's relax one of the assumption that, we initially regarded this requirement that, none of the jobs do input output. So when you do input output, when you require input output, a program goes from a running state to a block state. Here, all on all the previous examples, all the programs were running between switching between ready state and running, ready state and running. But what if one program requires an input output? Well, then it has to move to a block state. Now, let's look at this example. Here, when a job comes, when a job arrives, you actually give it all the time that it needs till it completes its job. So here A arrived, and then A had some input output that it needed to do. So you move it to the block state. Nothing gets done in the processor. And this is, A doing some input output. As soon as input output is done, A comes back to the processor and starts running. This would be, let's say, this would be your CPU, and this would be your disk. So it is running in the CPU. It has to do some input output. It fetches some input output from the disk. CPU is not doing anything in the meantime. And then A runs again, and then it requires some input output from the disk. It does so, but again, the CPU is not doing anything. And then A runs again, it goes to the disk. Again, CPU is not doing anything. So if you look at this, this is poor use of resource, because now A does complete its work in 90 seconds, 90 milliseconds in this example. But imagine B takes, B has to wait. The response time is bad. The turnaround time is bad. B has to wait really for A to finish its job. But now let's say, look at this. So this is again the CPU and this is disk. So A came first. They require the same amount of time. That's fine, hypothetically. But let's say A arrived first. A starts its job. And then at this point, A needs to do some reading from the disk. Well, it can do that. Nobody's stopping it. But the CPU doesn't have to sit and wait for A to finish. No, CPU can actually do something else in the middle. Right? So what you're doing is you're allowing for overlap of the jobs to take place. Why? So that, the CPU is used all the time. It doesn't sit there and just burn clock cycles without doing anything. So B starts working, and then A, because, A has maybe has the same priority as B, A is ready again, so you run A again. A came first, so A has the right, fine. So A starts again. and then A requires some input output. Good. Let it go, and then you start running B again. And when A is blocked, it goes back, it's ready, it comes back in the ready queue. A runs, and then B runs. And then, if you switch something, like do some switching, you seriously improve the CPU's utilization, not just in terms of the time it takes to the turnaround time, but also in terms of uh, not only just how much the turnaround time, but also response time. Okay. So when a job initiates input output request, that's fine. You can do your input output. The job is blocked, and the schedule is another job to run on the CPU. And when the input output completes, an interrupt is raised, and the OS says, fine, I'll go back to the block state, and it goes back to the ready state, and I can run it again, as you saw here. And that really improves your this switching between different jobs helps really improve is efficiently uses your CPU. It also improves your response time. It also improves your turnaround. Okay, so that's pretty much for this chapter. Um, Inshallah, see you for chapter 8, which is the multi-level feedback queue, where we no longer believe we know how much time it takes for the job to finish. Okay, it also won a Turing Award, so it's really very honorable and respected framework um, back then. Thank you very much, and have a good day. Bye-bye.